Thank you, Amita, for a very nice talk. Some questions from the audience first.
May I go ahead?
Yeah, please.
Hello, Professor
Yes,
Amita. Yeah, I'm Ambrish Pandey. Thanks for a very nice talk. I just wanted to follow. What kind of equations do you solve? Like, are these full MHT equations or something different kind of?
Okay, in the simulations you're saying?
Yeah. It's simulation part.
Simulations are particle in cell codes. And
Okay.
then, like you have particles,
Okay.
etc. And
Okay.
so they follow, they feel the Lorentz force. And the force, the force is evaluated because of the electric and magnetic field generated. So what is done in this particular scheme is that you have a grid and you have particles. And these particles are not real particles, they are fat particles. So the collisional effects are not, cannot be simulated. So it's similar to molecular dynamics, but not quite like it, because the particles are not real. They are fat particles. So two charged particles can penetrate and go cross each other. Okay. And they're but the location of the particle is at the center of the cloud. And what one does is that as the particles are moving, so you have the grid, so you calculate through interpolations what is the contribution of the charge at the grid points, and from that you evaluate the electric and magnetic field, and the currents are evaluated at the grid points. So then from that you can evaluate the electric and magnetic field at the grid points, and then they are interpolated back at the particle locations to evaluate the force for the next time.
Okay.
So that's how the loop works.
Okay.
It has certain advantages because you don't have to take the same number of charge or particles. Because in laser plasma, it will be 10 to the power 22, 23 particles per cc. You cannot simulate those many particles. But you can have a finite number of particles, million or something like that, which have the same charge to mass ratio. And the collective effects will be taken. This is the beauty of the plasma, that because of this long range interactions, the collective features are very well captured by this particular scheme. So this PIC scheme is relevant only for plasma beating. Where collisions are involved, very sharp and all that, then PIC cannot take account of that. So there people use molecular dynamics simulations. So that is why this method is only restricted to plasma physics.
Yeah, I will have a look at the paper, a recent paper, to get a better idea. Yeah. And another question. When you study plasma, so how the properties of these plasma which you study are different compared to plasma observed in solar convection, for instance. So you treat different kind of plasma, or are there some universal properties? I mean, I'm not really familiar with this field.
Basically, plasma spans a very large range of density and temperature. You look at fluids like hydrodynamic fluids or gases, or solids, neutral. Then, what is the highest density fluid is mercury, let's say 13.6 grams per cc, and the densest and some lightest would be alcohol. So you will have a density range of, let's say, 1 or 2 orders. Whereas plasma medium is, the temperature is, I think, I forget now, something like 15 orders and density of 25 orders. And yet it behaves like a plasma. You have to use the same equations. Of course, there are differences in the sense in certain regions, relativistic effects will dominate. In certain very dense plasmas, quantum features may come in if your de Broglie wavelength is compared to the plasma typical scale lengths. So these effects, and then you have to use relevant equations. But otherwise, the plasma medium spans a very huge range. So
Okay.
this is the...
Okay. Yeah, thanks. Thank you.
Okay, I think I can just add a little bit. So since I kind of worked at solar stuff, so solar is both ions and electrons are mobile. I think Amita's thing is mostly electrons are mobile, right? Is that correct, Amita?
That is correct, but I mentioned as if you wait a long time, like in laser plasma also the ions started interacting.
That's right, but in solar ions are doing it, and it's MHD is good for solar, I think.
Because you're looking at time scales which are where ion can respond. You're looking at very long time scales. In laser plasma, there's an origin of the event. Plasma has been created. There's an origin. There's an interaction with very rapidly oscillating laser fields, which can only drive the electrons very fast. So that.
Yes.
Okay. Yeah. Thanks.
So other questions? Okay. So I'll ask. One few questions. Going to larger scale compared to what Weibel or things are giving, is it because of some kind of Kelvin-Helmholtz large wavelength is coming in the beginning itself?
There's no variation along the flow direction in this case.
I see. Transverse. I see. So what is, okay, I didn't follow the math. What is causing that transverse direction movement of instability, or rather of the effects?
Actually, there is current separation only, which ultimately is happening. But the point is that when you separate currents, like annexite instabilities, then you have to couple it with a dissipative mechanism so that the excitation is faster, as I showed in the boundary terms. So here the radiative effects provide such a coupling.
I see. So is it that these two beams are breaking into filaments in the transverse direction and they're just propagating?
Yes. Weibel is essentially that, but the breaking size of the filament is skin depth. Whereas here, you can see that the magnetic field accumulates at the edges of the beam. This was the beam size, and this is like at the edges there is a magnetic field.
I see. So how is it growing in the transverse direction? So what happens next?
So let me show you the movie. Yeah.
So the color bar is the middle one, right? The middle band is the color bar.
Middle band is the beam. This is the electron density. So this is
no. Color bar is inside the block itself. Okay.
Yeah, sometimes they do this, and then this is prepared. Every time, every student I have to give this. So they learn, and then by the time they learn, they leave. So new one comes, you have to teach them again.
I see.
So
where is it happening now? Inside some? Okay, I see. Okay.
Like
so transverse, let's see.
And this is radiation. If you look at the B field is in the Z direction, and there's a EX. So, and the propagation direction is this. This was the beam region. This is basically electromagnetic radiation which is coming out. But then there is this part remains stuck with the beam. Even after the beam has gone, there is a part which is non-radiative, this. Even after the radiation is gone.
I see. So radiation is electromagnetic, both E and B, right? Which is generated.
Yeah, here when the radiation was going here, this is the magnetic field this is the X direction, this is the Y direction. Magnetic field is along Z direction, plus minus Z
I see.
And the electric field is in the X direction. There's also an EY component, which is electrostatic, which is responsible for the density variation. See, here you will not see any electron density separation as of now. So EY has not gotten generated. But later on, you will see. Now there is an electron density separation which is happening. So EY is now getting generated. So as up to now, it was EX and BZ. And this EX and BZ and propagation direction is this direction. So this is like a pointing flux going like this out.
Okay, so it's all electromagnetic coming from that.
Yeah, coming from because the current inside oscillates. The imbalanced current basically oscillates.
I see. So that's antenna which is...
and it acts like an antenna. It starts oscillating. I have chosen initially in one direction, but it starts oscillating. That was the observation.
Okay. I see. Great. So anyone else?
Can I ask a question?
Yeah.
Please.
Yeah. So I'm happy that my computer is now giving out. I tend to think in the electrical engineering terms. We have this plasma thing.
Kind of thing?
Yeah. Well, there are two things. I'll jump to the application part. Okay. In transformers, we have these windings, and they're very close to each other. They are copper wires.
Yes.
And they are typically wound around core material.
Yeah.
And that's the action there, right?
Yes.
So and a typically transformer, a large power transformer can sit in the field for 50, 60 years. That's the record. Some Japanese are claiming that in India there's a transformer that is sitting there for 70 years now, 60 to 70 years. So what I was my question is that what are the physical repercussions in the sense that if a copper wire is there and it starts ready, so do we expect that copper wire to become brittle or something because of this physical action? Meaning,
okay. I didn't get the first. I was one. Actually, let me tell you another thing. I'll come to your question first. But before that, let me mention it. I had forgotten to mention it. It's like a leaky waveguide. You can look at it as a leaky waveguide. It is radiating. And then this beam is like a leaky waveguide. Now, coming to the question, you are talking about transformers, right? So there, what is the question about? It has.
So the question is this, that in transformer we have coil that is a copper wire wound very close to each other, and it matters a lot what is the distance between the coil, because in typical electrical engineering terms
they must be having some insulation around it, right?
Correct. So they usually put in over copper, they put paper which is whatever, there's some insulation paper. Yeah. And the thickness of that paper is a very crucial factor in the total design. Yeah. And even with the best of the workmanships, sometimes there are very small holes in these papers, and they cause failure of design. I'm talking about large size transformers.
It can. There can be current. You can have a burst.
Yeah. So that's failure, right? Yeah. So what people try to estimate is what should be the ideal. These papers are very expensive. They're almost like currency notes. They are made through special processes. They're almost like security papers. That being said, the thickness matters, and the cost variable is accordingly. What happens in the field, and I can tell you I'm just from a practicing point of view. What happens is that if the transformer fails, they'll bring back the job and they'll remove the coil, and then they'll rewound these papers. So that's a very expensive thing. So to have a design parameter based upon what you said, they are concerned about plasma within the coil, and they want to see it through several layers. So they have these special heat measurement devices that kind of read what is going on inside the transformer, these maintenance people, usually. So on that count, your comment is important. I mean, I'm not saying that your comment about what's the physical thing that's happening there. It's damaging.
Actually, it must be ohmic joule losses. This ohmic heating can liquefy the copper wires or maybe ionize them also. So then the fields can leak through the paper.
Okay.
Because there is a skin depth over which in fact, they talk about surface plasmas. Metal also is a electron carrier, right?
Right, it is. And
so electron density, you will have plasma frequency associated things there. So it is that if you have a electromagnetic, there is always a evanescent electromagnetic wave. Sorry, not wave. Electromagnetic. The field will leak through a distance of c by omega p.
Okay.
Something like that can be.
Right. Okay. And because you were talking. Yeah. Well, I'll let you finish first because it's important for me to hear.
That is what. And then if it leaks, and supposing your winding is closer than that.
Usually it is, because it's an important design parameter in any. Meaning nowadays, when you instead of these large power transformers, we are talking about very small transformers, smallest, and all these miniaturization techniques. So instead of these wires, they'll put in a special coating on these small copper, like varnish, and minimal. These are expensive fluids.
So heating is important. How much of heat current you're passing, how much of joule heating is being created. So
joule heating is something that I should be concerned about, right?
And then
right. And in terms of the antenna thing, you were saying something, and I kind of missed that. There's some.
What I'm saying is that this is a beam propagating in this direction, and there's an imbalance current, and this imbalance in current basically we have observed in simulation that it oscillates. So even though earlier the current was all in this direction, it turns around and it oscillates. Now oscillating current radiates wave outside. So this is how the radiation happens, and that is why finite current in the beginning is important. And once it radiates out, it has dissipated the beam energy and dissipated coupling in these kind of modes because these are negative energy excitations. The instability doesn't require energy to excite. In fact, because the beam already had energy, it in fact is a negative energy mode. So the dissipative energy helps in exciting the instability. So radiative dissipation is important.
And there should be a way. Because we're talking about now antennas, there should be a way to capture this thing. Like just in case we are interested in knowing something about what kind of antenna, these people want to. There's some people who have started claiming that these radiating modes could be used in communication lines, and the so-called smartness to the to the communication.
People are making plasma antennas because they are useful in that sense that your regular antenna, you have fixed your the geometry is fixed.
Yeah, and
you can do only certain tasks, but plasma you can ionize it, and you can choose whatever geometry you want and whatever, and then it will do as per your desire. So there will be some maneuverability involved if you're trying to build an antenna using plasma device. So that is
right. Okay. So there could be design, meaning because your simulation tends to give a like a cable kind of
going on specifically to have use plasma as the as antennas.
Antenna, right. Thanks so much. Thank you so much.
Thank you.